Okay, so good morning and welcome to this hands-on session. I hope that this will help you realize what is involved in creating an RV tool. The material was planned originally for a longer session. Okay, we're going to go a bit faster than usual through the material, and some exercises we'll have to leave out. You can obviously follow up and continue working on them on your own, even maybe tonight, and if you need, I can help you tomorrow. But obviously we just have 1.5 hours. Okay. So at first I will start by introducing the system we will be working with, and then as we go along, we'll start doing the exercises together. Okay? Sounds good? Perfect. Okay. So I'm not going to introduce monitoring again. I'm sure you've heard a lot about monitoring so far. What I will be introducing first is what we call the financial transaction system. We call it FITS. Okay, this is just a very simple system which we use for students to try out monitoring. Okay, so the idea is that it provides like a virtual banking system, okay, where users can make transfers, they get approval, they get blacklisted, disabled, enabled, some very basic stuff. We have two kinds of users. We have administrators who can perform privileged actions, and we have users which are the normal users who may open bank accounts, make transfers, etc. What is interesting are these three. We have a status, so they can be whitelisted, graylisted, and blacklisted, which obviously will affect what actions they can perform. Okay. We have the type. We can have gold, silver, or normal users, and they can be active, disabled, and frozen. So, for example, a property might be that a disabled user should not be able to perform any transfers. Okay. So then we have two other concepts, apart from the concept of a user. We have the concept of a session. So a user will log into a session, then he can do some actions during that session, and he can log out and leave that session. Then we have the concept of an account. So users can have multiple accounts with money inside the accounts, and then we can transfer money from one account to another. Okay. This is not important for your work, but just to have an idea of the structure of the system, we have these five modules, which we will be interacting with. Okay, obviously, user account and user session will be the most that you will use. And here are some properties of the financial transaction system. We will be working with, mostly for the examples, for the exercises, with number 2 and number 5. So I will be introducing those, leaving the others for your work as exercises later on. So number 2 is a very simple property, which will be handy to start off with. So the transaction system must be initialized before any user logs in. Okay, so as soon as you detect a login, you have to make sure that the system has already been initialized. That is the simple property. Another slightly more complex property is the fifth one, that once a user is disabled, that user cannot withdraw from an account until being activated again. Do you see a difference between property 2 and property 5? There is a substantial difference. Any ideas? Sorry. So the difference is with the level of the property. So property 2 is about the general system. Okay, any user cannot perform a login unless the system has been initialized. Property 5, on the other hand, deals with each particular user. Okay, so one, you just need one monitor. The other one, conceptually at least, you need one monitor per user. Okay, this will make a difference in our implementation. Okay. There are many other properties, and obviously, I'm sure we can find many others. But at this point, it's not the point. We'll be here just dealing with properties 2 and 5. Okay. So what I would like you to do at this point, to make sure that everyone is on the same page, is to run the clean version of the fits. You should have the project ready to import from the exercises folder, which you downloaded from the repository, and have a look at the code, run it, okay, and you should see that there are a number of scenarios, 2 scenarios per property. Okay, one scenario which makes the property succeed, one scenario which makes the property fail. Okay, I will be going around like for a couple of minutes to see if anyone has problems. At this point, all you need to do is to execute the code, okay, and have a look at it to make sure that you have an idea of what it involves. Okay. Okay, so the next step, what we're going to do is to simply insert monitoring code by hand into the system. This is the most basic form of monitoring that you can think of. Okay, so we're going to simply modify the code to insert the monitors. So how do we do this? Obviously, there is the concept of an assertion in Java. Probably you are familiar with it. It's a good way. It's like the most basic monitor you can have. We're not going to use assertions in this tutorial just because assertions will throw an exception. And at this point, we don't want the monitor to throw exceptions. You might prefer that, that's fine. But for this exercise, we will have our own virtual assertion, okay? Which will simply like print something in the system.out, okay, in the console. So we'll just have this concept of verification.assertion, condition, and the error message. And that will be all from the assertion side. It will not throw any exceptions. Okay. Now, you will need some extra variables when you implement monitors by hand, right? So for example, in this case of property 2, if you want to remember that the system has been initialized, you will probably keep a Boolean variable somewhere, right? To remember that initialization has taken place. So you can use the verification class, you add static fields to it to remember the state of the monitor. Obviously, this is not the right way to do it. This is the first step of creating the monitoring system. As you will see, this is not the right way. But for this exercise, we will do that. Okay. So if I have the simple property of A should happen before B, okay, what should I do? So on initialization, okay, I should make sure that my Boolean is false. That is initialization. Then, as soon as event A happens, I need to set the Boolean to true. So I remember that that has happened. Okay. What else? What do we need to do next? We need to make sure that once B happens, okay, we need to assert that A had happened. Otherwise, oops, something went wrong. A didn't happen before B, right? Okay. As you might notice in the code that I have given you of fits, you have this idea of initialize verification. Okay, so you need to put there any code which you will use to restart the monitor. For example, setting the Booleans to false. Okay. Now, remember that that we saw the difference between property 2 and property 5. Property 2 was a global property about the whole system. Property 5 was about every individual user. Okay? So, whenever you have this concept of for every user, okay, what you need to do is to use some kind of either hash map, okay, which we'll be using this for simplicity, or you might like encapsulate a monitoring object with the user information. But to keep it simple, we'll just have a global hash map to store the information about each monitor. Okay, so now comes the part where you start working. So what I would like you to do is start with the clean system, okay, and try to implement these two properties, at least property 2, okay? So you should have something like the code I showed you, where you have a Boolean variable to remember if the system has been initialized or not. And then you need to call verification.assert whenever someone is trying to log in, right? If someone tries to log in before the initialization of the system, then you should report an error, okay? Okay, so one of the first steps you could do is to go inside the transaction system, find the initialize method. Okay, there are many places where you could put this. This is just one place where you can place it. Okay, and you have to remember that the system has been initialized. Okay, so somewhere then you need to set the Boolean to true. Okay, so here I'm calling verification transaction TS initialized, okay, which will set the Boolean to true. Yeah. If it's accessible, yes. The idea is that we're moving towards like having a monitor which is separate. That's why it's fine at this point to have some duplication, because eventually these will be more separated. Okay. Everyone managed to do this first step? So the next step would be to go to the login part, okay, and make sure that the Boolean has been set to true. So you should end up in, for example, the open session method, amongst others. And you can put the verification code something like this. Verification.assertion, get whether the system has been initialized or not. So if it hasn't been initialized, then you should report that P2 has been violated. Obviously, remember to reset the Boolean with the verification initialization. Okay. Okay, we'll give a few more minutes. Obviously, this you can continue during your own time. And those who are ready from property 2, you can try property 5 at this point. Okay, so to make sure that your property is working, when you run the system now, you should ensure that in the third scenario, it reports that P2 has been violated. And in none of the other scenarios, it says that. Okay, so it's just in the third scenario that it reports a violation. Okay, which is this one over here. Questions or problems? Okay, so unless there are any questions, I would like to continue moving forward, even though I know that some of you might not have managed. Okay, the idea is to give you a taste and then you can continue, and I will be available for anyone needing help. Okay, so this exercise, I hope it has convinced you that this is not a very practical solution. Going through the code and inserting pieces of code here and there is not the right way to do monitoring. Okay? So and obviously things get even worse when you try to do property 5. So property 2 is just a boolean, okay, that you have to add. Property 5, you will probably need some kind of hash map or hash set or something like that, which will make things more messy, okay? So you would need to add this, for example, set of integers, remember who has been disabled and not, and so on, okay? So the take-home message from this are these points, okay? First of all, it's the lack of separation of concerns, okay? We need to somehow separate the monitoring code from the system. Otherwise, the extra assurance that the monitoring is adding is not really like separate from the system. So might as well improve the system on its own. The advantage of monitoring is when you separate the concerns, okay? So hopefully the same mistakes that you did in the system will not be repeated in the monitor, right? And this also has all the disadvantages of poor modularity. So if you want to change the properties of the system, you will immediately have to change the system itself. Okay, you cannot change the properties without changing the system. Even worse than that, if you want to run the monitor, for example, in offline mode, so separate from the system. So let's say you have a system, you leave it running for a week, and then you want to check the results after. With this approach, you have to modify the system completely, okay? With the approach that I will show you now, using another technique, you can keep everything separate, and if you want to change the system, you don't have to change the monitor, and vice versa. If you need to modify the monitor, you don't need to modify the system, okay? So ready to move on to the next step? Okay. Okay, so this is the introduction. We'll start first by explaining what are cross-cutting concerns. So usually when we organize object-oriented code, okay, we identify some concerns, some modules, okay, so that we separate the system. And usually we manage to create a class for each concern. So you might have a class for a user, a class for the bank, and so on. Okay, a class for the session, perhaps. The problem with this is that there are some other concerns which will, the technical word is cross-cut, which will like overlap with all the other concerns. For example, if I want to log some data, some information in a database, you would need to insert the logging code inside every other concern, right? Inside the user object, inside the session object, inside the bank object, okay? So sometimes it's easy to organize, but with some concerns, it's not possible because you will have a lot of overlap, okay? How do we solve this? One approach to solve this is what is called aspect-oriented programming. So what we call an aspect, okay, is this cross-cutting concern, which we will program as a separate entity, okay? And from a single file, we can then modify the whole system without actually touching it, okay? This is why this is so convenient for monitoring, okay? Questions so far? Obviously, feel free to ask at any point. Okay, so how do we do this magic? Because this sounds a bit like magic. How does it work? So basically, aspect-oriented programming exposes a number of points in the program. For example, method entry and return, class initialization, exception throw, exception handling. There are many others, okay? And it gives you a handle at these points. So if you like, you can insert some extra code that you want inside those places without actually going to code yourself there, okay? So it's like giving you like some space where you can insert code. Now, these points are called join points. I'm telling you, like, I'm using the actual words, so you at least listen to them and have an idea of what they mean. These are called join points. Then, one level up, we have point cuts. So point cuts are sets of join points. So we have a way of, for example, saying I want to match the pattern that at every exit of the purple method, okay, I insert some code. So this gives you like the power to speak about a number of points at the same time. You don't have to program each point individually, okay? Then the last concept is advice. The advice is the piece of code that you would insert at that point that you made available. So let me recap. We have join points, which are the points available, point cuts, which are the matched points, which are of interest to you, and advice is the piece of code which you insert at a particular point cut. Okay. Okay, this is just a summary of what I was saying. And we have an example right here. So I can say before method login, okay, this is actual code, okay, from a spec.j. Log, add logging in. So that is custom code, the part in the brackets, okay? But this is actual code from a spec.j, the red part, okay? So this is a point cut. I'm saying for every call to method login, before it starts, I want to insert this piece of code. Okay? And that is what is called the advice. Okay, that is the piece of code which we will be inserting. And this is an excellent way for monitoring to separate concerns. Okay. So now how can we use AOP for our fits system? So what we can do is this. We can, for example, say before login, set the verification as logged in. Okay, so instead of going to the login method and adding verification, blah, 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 you simply go through the aspect file. You will see that now instead of Java files, you will also have AJ files for aspect.j. Okay? And you simply write this code in a single file. So from that single file, you have all the information about the monitoring that is going on inside your system. Okay. Now, SpecJ obviously is just one particular tool, which happens to be the most popular for Java. That's why we're using it. But I want you to separate SpecJ from AOP. They are two different things. Okay, SpecJ is just an implementation of AOP for Java. It has good support from Eclipse and so on. And in the next slides, I will give you some details about SpecJ. I will not go into all the details, but I will give you just enough for this session. Okay. So this is what SpecJ looks like. So we'll have, instead of class, you have aspect. Okay. You have those point cuts in yellow, and you have the advices, which is your code that you want to insert. In this case, one is before a method call, one is after a method call. You have some asterisks, which means that they will match anything. So you have the first asterisk, which will match the modifiers and the return type. The second asterisk will match the kind of object on which the method is called. Okay. Obviously, you can also use the asterisk for the method name as well, but it might not be very useful in our case. Then you can match the parameters, and you can insert the advice. So how do you start matching the parameters of interest? So the first object that we're going to match is the target. What do we mean by the target? The target is the object on which the method is called. That will be called the target. So if you say before, and in the brackets you write the variables that you're interested in, and then you say target X. So it means that now shape.move, that shape will be matched, which will be bound with X. Okay. Similarly, we can bind the return object, which might be very convenient when monitoring. And also, we can obviously bind the parameters themselves. Okay. This would be like a whole example of SpecJ, where you are binding the target, the arguments, and the return object. Okay. Simple enough? Questions? Okay. So we're going to do the same exercise as before, but now instead of going inside the code yourself, okay, you're just going to stand outside of the code, starting from an aspect file. You will match the interesting methods, okay, and insert your code there. So now start from the second exercise, which is called AOP something. Okay, you should have an aspect file there and start editing it to add support for these properties. Let's start with properties 2 and 5 again. Okay, so I know that some of you are having some problems with AJDT. Unfortunately, it's not possible to solve them at this point. Okay, there might be some versions of Eclipse on the AJDT webpage with AJDT installed already that might be helpful. I'm not sure if they exist, but I think there should be. Otherwise, we'll have to resolve the issue later on. Okay, the time is running very fast, so I wish to at least cover this SpecJ and the next step. So you should have something like this, okay? And if it's working correctly, you should see these small orange arrows, okay? Those small orange arrows signify that your point cut has been matched with a particular join point, okay? So if you see this cross references here, okay, you will see where that point cut is matching. Okay. Okay. So then once you run it, okay, automatically this code will be introduced. So now we didn't modify the system. Okay, we added our own classes, like the verification class, that's fine. Okay, we didn't touch the code inside the system, but we simply put the glue inside the aspect file. Okay, so you will just see this, and you know where in your system the code is being inserted. Okay. So here in this method, as you can imagine, this is just setting the Boolean that the system has been initialized. Here, I will simply check whether the Boolean has been actually initialized before. Okay, by checking the Boolean. Yes? So that is a choice. Okay. I will not talk a lot about it today, but it's a choice whether you insert the actual code like this in the other properties inside the aspect code, or whether you have like a class with all the methods, and from the aspect code you simply call that. I would tend to prefer like putting all the code inside a class, and from the aspect you just call it. So you have all the variables and so on inside classes as usual, and the aspect file is simply gluing everything together. Okay. Obviously, you will need to do something similar eventually for property 5, okay, which will involve also using some kind of hash map, okay, to keep track of every user. Unfortunately, we don't have a lot of time, so I'm going to move on to the next part. Okay. Okay. So our journey is like this. We first inserted code manually by hand inside the classes. Now we went a step further by inserting the code through aspect-oriented programming. The next step is to not generate the aspect-J code ourselves. Okay, so we're going to write the properties using a slightly higher level language. It's not, as you will see, it's not very high level, but we can take it further from there. Okay, but we're going to make one step more now. We're going to write the properties in another language, and we'll have an automatic compiler which translates that specification language into aspect-J code. Okay, you see, so we're going one level of abstraction up. So first we separated the concerns. Now we're going to increase the level of abstraction. I think these are the two main tools of runtime verification, okay, which is separation of concerns, the level of abstraction. What is the advantage? The advantage of these two is that they would reduce the chances of making the same mistakes that you did when you coded the system. So the idea is this: if you program your properties using Java code exactly as you would do in the system, chances are that you will make the same mistakes. So that's why we're going to use a higher level language. As you will see, this is not higher, like the step we're going to take is not big. But then using this, we can go to automata, for example, or you can use regular expressions, or you can use LTL, or whichever logic you will like to use to specify the properties. And then the translation from the mathematical notation to the Java code will happen automatically. Okay? So now you're going to have to do two things in this part. You're going to need to write the properties in the new language. Okay? So you're not going to program the properties inside Java now. You will write the properties using the new language. The second thing would be to write this compiler. Obviously, now we don't have the time to write the compiler, but I will show you the code of the compiler. Okay. Okay. So what language are we going to use? This language is called the guarded command language. And it's very convenient because it's like a set of rules. What is a rule? A rule is simply an if-then else statement, basically. Okay, so you have a condition. So if I detect method move, and this condition is satisfied, for example, dx is greater or equal to 0, blah, 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 do some action. Okay, so we're going to structure ourselves by using this approach. Okay, if an event happens, check the condition, run this action. Makes sense? We're going to have a script file. In the script file, we will still need some Java code, okay, to support these rules, obviously. Okay, we're going to have what we call verification code, which will be like the Java support code. We will have the prelude. This will be added to aspect-j, and we will have the rules. You will see an example very soon. So let's see a rule. What will be a rule? So an actual rule would look like this. You say before the method is called, this we will take like the default would be before. We will match these parameters. Okay, so this is very similar to aspect-j, but not quite aspect-j. We try to simplify it a bit more. Then you check these conditions on the parameters, and then you perform this action. These are a couple of more examples. And then we have also, you can also match the target there, you see. So you can match the object on which the method has been called. And you can also leave the condition empty if you don't need it. Okay, and also the parameters you don't need to define, again, if you don't need them. Okay, so what I would like you to do now, just a quick exercise, is to try to express property 2, okay, in terms of GCL. You should already have some examples. Just look at the code and add this GCL. We will get that. No, this is our own compiler, which I will show you, and you can edit yourself. Okay. Okay. I know I'm interrupting you every time, but unfortunately, we don't have enough time. Okay. So what I'm going to do now, I'm going to ask you to import the solution of the RV tool. So this is the compiler now. Remember that we didn't write code which is directly compilable with aspect-j. We need our own compiler at this point, okay? Which will take the code, the GCL code, and translate it into aspect-j code and Java code, okay? Since ideally you would have like coded some of it yourselves, but I'm going to show you some code from it. So in your Eclipse, you should have something like this: my RV tool solutions. And this does not need to be an aspect-j project. Okay, everyone got this project? Mm-hmm. So let's have a look inside it. So the interesting part for this session is this GCL package. Okay, and what I would like you to do is have a look at the methods called toAspectJ. toAspectJ. There are some methods inside the GCL script and inside the rule classes, which are responsible in generating the aspect.j and Java files. Okay, have a look. So you have an idea what it would involve to create your own compiler. Okay, the idea of this session is to show you the under the hood of an RV tool, how it looks. Obviously, a very basic one. Okay, so if you open the toAspect.j method, you should see something like this. Basically, it's iterating on the rules, and for each rule, it's generating its toAspect.j code. Okay, so then if you go to the rule, you should again find the toAspect.j. And obviously, this is where the magic happens. This is where the aspect.j code is generated. You see it's reasoning about the args, about the target, and so on. Okay? So what I would like you to do now is to use this project to compile your script. Okay, so you should have a script. If you don't have one, you can simply use the one that we have here. You see, you should have this script file over here with the GCL solution. This is the code written in GCL, and you can compile it using the compiler. So you get the aspect.j code. Okay. So let's make the next and last step for today. So we started with manually inserting the monitor inside the code, right? Then we went a step up to use aspect-oriented programming. Now we introduced the concept of a compiler. The next step is to increase the level of abstraction. So now instead of using a GCL, okay, the GCL language, we're going to use automata. I guess all of you are familiar with automata or finite state machines. And we'll define properties in terms of automata now. Okay, and our compiler will just translate it into GCL, which is very easy, right? What would you need to convert an automaton into a GCL code? Just one variable to remember the state you are in. That's all. Okay. So we're going to have monitoring states now. So GCL, through the use of Java variables, it allowed us to have what we call implicit state. Okay, so through the variables, your monitor will have its state. Okay. But as you noticed, a lot of what we did in the AOP, we had to do also in the GCL. Okay, we had to write, handhold the system to tell it how to proceed. But now, we would like to explicitly, okay, using the language itself, express the state. So the state, from being implicit, we're going to make it explicit by using automata. Okay? So for example, if I don't want any transfers when the user is logged out, what can we do? So we have this automaton which starts in the logged out state. Okay. If the user logs in, it's fine. Anything can happen there, we don't care. If the user logs out and makes a transfer, something went wrong. Okay. Does this make sense? The advantage here is that as soon as you look at this, it's easier to understand what's going on, at least in my opinion, rather than having DGCL code, which you can have obviously the same thing, but it won't be so visually obvious what is happening. So how would we write this into code? Our language will look something like this. We kept it simple again, and you have the compiler inside that rvtool project. So we named the automaton. Okay, so the property will start at state LO, logged out. From LO it goes to logged in LI on login event. From login event it goes to logged out on logout. If it detects a transfer from logged out, we end up in the bad state. When we compile, now I think you can start to understand what is happening inside, right? When you compile that transition, what is actually happening inside is that we have like a spec.j code with that point cut, with that event, right? We're taking before and call as the default, and we copy the event. Then what we need to check is this. If the monitor state is inside S1, when that event happens, then move the monitor state to S2, right? So the translation is not very complex, but the advantage of going up the level of abstraction ladder will help you when you create the properties, when you express the properties. Now, obviously we can make it a bit more interesting. Instead of simply having events, we can also have conditions and actions like before. So on each transition, we can check, for example, that if S is private, then protect F. And this is also an interesting concept in the sense that the monitor can also attempt to fix the situation. You see, so the monitor is calling f.protect. So far we have been using actions to update the monitor itself. In this case, we actually are updating the system, not just the monitor. You see? We are doing something to fix the situation. And the code would look something like this. Okay, so now instead of simply having the event, you have like a rule on the transition. Okay. So we still have some part of the state which is explicit in terms of the automaton states, and we still can have some state which is implicit in the variables of Java. Okay, and the change in the code is very simple. Instead of just having that if statement, we just add condition and we add the action. Okay, so I added those two parts, the condition and the action. Okay. I'm noticing that in the slides, the use of implicit and explicit is the opposite of the way I'm using it. It's the way you see it, okay? But if you want to see the circles of the automaton as explicit, but in this case, it's called implicit, the circles, right? The automaton states. Okay, now obviously, some properties will benefit a lot by using automata. Some properties are not, you cannot really use automata for them. So for example, in the case of property 1 of the fits example, when it says a user should be accepted only if it's a gold user, for example, if you use an automaton, it doesn't really help. If you have property 2, the one that you have to initialize before logging in, it's also not a very interesting automaton. It will just simply have two states, initialize and login. Okay? But there are some other properties which might be interesting. Now, as you might recall, property 5 was different because we had the concept of a for each user. Remember, the property was applied for every individual user. So far, we didn't provide any support for that in our language. But what if we can also provide support for that? Okay, so that the user doesn't have to program hash maps, because this is something which will happen frequently in OOP programs, right? So now we're going to add this concept of a for each user u. And we're going to use the target of the method, of the event, okay, to bind that object on which we'll do the replication. So every time we encounter a new user, the monitor will automatically spawn a copy of itself, okay, so that it starts monitoring that particular user. So you have for each target, user u, and now you have u.login, u.logout. Okay, so that u will be used to replicate monitors. So now what will happen is this. Whenever we are updating the monitor, okay, we'll check if the monitor has that object already in its system. Okay, if we find that object, we will check the state of that object, of that monitor, okay, and update it accordingly. If not, we will create a new monitor. Okay, and it happens like this: monitor.addTarget new monitor. Okay. Okay, I know we don't have time for all this. I will give you some time to express a couple of properties into automata. Okay, have a look at the compiler of automata. It's also included in the solution of the RV tool. Okay, and today that will be the end. Obviously, the story does not end here. On top of automata, you can go to regular expressions. You can go to LTL, which are both translatable into automata. Okay, so the level of abstraction that you want, it's up to you, but the idea remains the same. Okay, so I think the two main take-home points is this: if you are implementing RV, make sure you have enough separation of concerns and enough level of abstraction. Okay, at least from this point of view. Obviously, there are other aspects such as the overhead. You cannot simply introduce any level of overhead that you want in RV if the monitor is running alongside the system. But from the point of view of this session today, where we focused on building an RV tool, the design conceptually has to make sure that it's separating the concerns, okay, and introducing a level of abstraction which is comfortable enough for the person expressing the properties. Okay, so we will have another 5 minutes working on automata, okay, and then I will conclude the session. Yes? Yes, I'm sure there are. I don't know them by heart, but I'm sure if we ask the other, one of the other lecturers, there are a number of tools. But personally, I'm not a big fan of LTL. There is some implementation also with your code, but I'm more like the automata person than the logic person. For the automata, for example, there is Larva, which is a tool from the Maltese university. But there are many others supporting automata. And actually, one tool that you should have a look at is JavaMop, which supports a number of logics. Okay, so thank you for cooperating in this session and trying the exercises. I'm sorry about the frustration AJDT has caused some of you. Yes, sometimes AJDT and Eclipse are not the best solutions. Obviously, you can continue working on this and asking me for the support that you want over the next day and even after by email. Hope you got the idea of what it involves to create an RV tool. And I hope that you find it useful and maybe you apply it somewhere, maybe, who knows, even in industry. Okay. So thank you, and I will see you tomorrow.